All right, but as for today, continuing through our more identity stuff, basically. All right, double angles and half angles. And you'll notice that as we do more and more identities, you get better and better at them. All right, because a lot of it is practice, but it all comes back to some of those original stuff that we did in the very beginning of chapter 5. Always go back to the basics. All right, sines, cosines, all right, quotient identities, reciprocal identities. All right, they're right on your cheat sheet, and every time that's what we want to use. All right, so we had one more identity to look at here. And that identity oops. All right, so part C here. And the big thing about this identity is that we always start with the complicated side, and definitely the left side is the complicated side. And when we see this, what should come to mind? All right, our techniques, convert to sines and cosines, done. Common denominator, done. Factor, okay, factor how? What is it? Cubes, it is cubes, not a difference though, right?
Oh, no.
It's a sum. By definition, difference of cubes, sum of cubes, all right? So I actually see sum of cubes and, all right, as I saw many of you do, good job. X equals cosine theta, Y equals sine theta. All right, when you're already in sines and cosines, why not do that? Because we often see the algebra easier than we see the trig. And absolutely. All right, so remember, wash the bunny face. Same, opposite, always positive. And then all you have to do is identify what cubed makes y cubed, which is what cubed makes y cubed?
Why?
Y. What cubed makes x cubed? X. And I mean that is now if that was something like 125x cubed, then it'd have to be 5x, right? But I mean, these are actually pretty easy cubics to pull apart. And then the bunny. Right? Y times y times x times x to fill in the pieces. Now again, you can just have this written down, but I was like, it actually works really, really well. And again, the more you do it, the better off it is, which means y times y is y squared, y times x is yx, and then x times x is x squared, all over y plus x still. And then what do we see? The bunny ears might be getting in the way, but and what do we see here? Y plus x, y plus x. Which gives us y squared minus yx plus x squared. Okay, I don't think there's anything else I can do, because typically when you have a quadratic, what should you think next? Part of the polynomial dance that we're going to do.
Diamond?
Diamond, yes. All right, diamond, factor. All right, but FY, just so you know, I could attempt to diamond this, but this is prime. I mean, I can see it there, all right, that it's missing the coefficient in front of that YX. So this is prime, which means I can't factor this anymore. So back to sines and cosines we go. And then I can see if, now that I'm back to sines and cosines, if I can identify anything. What do we see there? Identity, fundamental identity, the fundamental identity. All right, you saw in your quiz, right, that we used one of the other fundamental identities, okay? And we use those ones as well, but the fundamental identity is should always be first in your mind whenever you have stuff being squared. So what we end up with then, sine squared plus cosine squared is 1. So I end up with 1 minus sine theta cosine theta. And then now we actually want to think back to where we're trying to end up. And we're actually ending up with sine 2 theta. That is a double angle identity. All right. And those are our new ones. So basically all of that we could have done before this chapter. And then we need to remember our new definition, which is sine 2 theta equals 2 sine theta cosine theta. So this is our new one. All right. Now notice this is pretty close. I don't have 2 sine theta cosine theta. So just like we adjust our fundamental identity sometimes, if I divide both sides of this by 2, I actually end up with 1/2 sine 2 theta equals sine theta cosine theta. And now I can substitute that in perfectly. 1 minus 1/2 sine 2 theta. And that is where we were going. So again, just a matter of messing around and algebra. All right. We use identities here and there, but so much of this is still algebra. All right. And I hear it constantly, the algebra of calculus, the algebra of trig. It's different than normal algebra. Yeah, because we're applying it. All right. We're taking it to the next level, which means the algebra helps us do what we're currently doing. All right. So we keep stepping up the process. All right. Given cosine theta is less than 0 and cosecant theta equals -√5, I want to find some double and half angles. With basically everything in trig. All right, so I got some stuff. What should we always do when you can first? Establishing identities, we don't do this, but basically whenever you have a number and you're finding other numbers, what should we always do?
The triangle.
A triangle, right? It's our go-to step, right? Is when establishing identities, that's a slight like kind of move away from it, but triangles really are what tie everything together. And it never hurts to make a triangle. Now, specifically here, we need to identify what triangle to make because we have the full 4 quadrants. All right, so cosecant. What is, okay, cosecant, I don't recognize cosecant at all, but what do I recognize that is related to cosecant? Sine, right? Okay, so I'm told cosecant of theta equals -√5. That means sine of theta equals what? 1 over. So it's just the flip. So -1/√5. Okay, so that one's helpful. Okay, so I have sine is negative. So what quadrants am I in with just sine negative?
3 and 4.
3 and 4. We're down here. Then I'm also told cosine is negative. Where is cosine negative? 3. Technically 2 and 3. And then I say, oh, where are both my fingers? All right, we are in quadrant 3. So I can make my triangle in that quadrant. And with my values there, sine is what over what? What is it?
Opposite over adjacent.
Opposite over
Hypotenuse, sorry.
hypotenuse. So, all right. Opposite over hypotenuse. Okay, so we got those pieces. All right. And don't forget, that says that we have a negative here, but since I'm in quadrant 3, I know that actually that negative is with the root 5. And then what wonderful theorem do we use all the time to find that missing side? Pythagorean. All right, so I have negative root 5 squared plus, that's the adjacent side squared, equals 1 squared. All right, so let's see what I'm at. 5. No stuff. A squared equals 1 minus 5. A squared equals negative 4. Square root. A equals negative. Oh, wait, what happened? The other way. Yeah, there we go. Oh, that's negative. Jeez Louise. Square root of 2 could be plus or minus, but I already know it is negative. So this becomes negative root 2. That was harder than I thought. Okay. All right. So my triangle is all filled in. All right. I have my sides. And, oh, geez, 2. My goodness. I'm struggling here. This is not holding my calculator. That's why it's killing me. Square root of 4, 2. All right, so, okay, I think we're good now. Now I'm like panicking. Need my calculator. Okay, no, it's 2. Okay, goodness, I have my triangle filled in. And then we were looking for some double angles, sine 2 theta, cosine 2 theta, and then some half angles. So let's start with doubles. Those are the easiest ones because they translate directly. All right, I cannot find sine of 2 theta. All right, all I have here is my triangle with angle theta. So any adjustment on the inside of the trig function, that does not mean you just double all these values. Okay, we have to use our identity in order to do it. Because if I was told theta is 37 degrees, oh, well then 2 theta is 2 times 37, 74, all right? And I could find that easy, all right? But if you're just given this unknown, all right, you need to make sure you use the identities. That's the biggest thing that I see people wanting to do. But the good news is that sine, which I already had 1 over root 5, and cosine, which is what's cosine in this case?
-2.
Oh my God, I set up my triangle wrong. Oh my gosh. Well, I corrected you opposite over hypotenuse and got so stuck on that. Opposite over hypotenuse. That's why those numbers were coming out messed up. My goodness, I apologize. I was like, wait, that's gonna be -2 over 1, which doesn't work because of the numbers. Oh, goodness. Okay, that all makes sense. Okay, which is -2 over root 5. All right, and then we multiply across, which gets us 4/5. There we go. Similarly, cosine 2 theta. Since we already found, now we found cosine. and we found sine, then we can just calculate away, plugging into the double angle identity there. All right, the interesting ones come in the half angles. All right, theta over 2 cosine sine of theta over 2 cosine of theta over 2. The half angles, all right, follow those formulas, and it's always 1 plus or 1 minus cosine theta all over 2. The tricky part is identifying whether it is a negative or a positive of that in general. That's the negative. All right, that's the hard part, because we have to identify the quadrant of the half angle. So we know that theta, all right, is in quadrant 3. So that means theta has some angle between pi, and actually there would be strict inequalities, and 3 pi over 2. All right, that's what it means to be in quadrant 3. There's some angle between pi and 3 pi over 2, 180 to 270. In order to do the half angle, right, divide it all by 2. That becomes pi over 2 less than theta over 2, and then 3 pi over 2 divided by 2 is 3 pi over 4. Hence, theta over 2, aka the half angle, is in what quadrant now? Pi over 2 to 3 pi over 4, what quadrant is that?
And the second one.
That's the second quadrant, right? 90 degrees to 45 plus 90, 135. All right, so 90 to it's somewhere between 90 and 135. So now we're in quadrant 2. Jeez Louise. And this is the big part. The sine is determined by the quadrant of the half angle. All right, so this plus or minus. So in quadrant 2, is sine positive or negative?
Positive.
Positive. Since we're going to do cosine, might as well do that at the same moment. Is cosine positive or negative? Negative. Negative. So, all right, so for the one we're doing, part C, this is a plus. For part D, this is going to be a minus. That's the most annoying part. The rest of it, all right, we've already done by identifying our triangle. We already know what cosine is. It was 3/5. No. Negative 2 over root 5. Once I have that, then it's just a matter of simplifying as best as you can what is underneath the radical. All right, so negative negatives becomes 1 plus 2 over root 5 over 2. And then we're gonna get ready to leave a change and flip it, so this becomes root 5 plus 2 all over root 5 over 2 over 1. Which, simplifying as far as I can, becomes that. Radical within a radical. It's all about exact answers, right? That's what we're always doing, all right? That's about as exact as it gets. I have a radical with a fraction inside it with radical in both numerator and denominator. Oh, that's a beauty. Should we bother rationalizing it? No, I think we're fine. All right, similarly, cosine of theta over 2. So we already determined that is a negative square root 1 plus cosine of theta over 2. These equations, all right, which again are on your cheat sheet, they're right called power reducing equations, all right? They don't have the square root on them on that generic cheat sheet. So that's a note you want to add on there, that in order to find the square root, the full half angle, all right, sine determined by the quadrant of the half angle and square root the whole thing. And then we get to do that again. And again, notice that the solutions are very, very similar. All right, positive versus a negative, and then that sign out front. I was like, once you found one, I mean, the others are very, very similar, and it's just a matter of simplify as best as you can. You always do your best to never leave it as a complex fraction, unless you're feeling really, really lazy. All right. Okay. Now, good news, bad news. So good news, we're going to come back to, and something that I saw in the quizzes, we're coming around to solving equations. This leads into the rest of what we're doing this semester, all right? Because from here on out, we're going to be solving equations. Now, before we get to the solving with full numbers, all right, this will all have full numbers, and we will get theta equals numbers. The problem being that it's a solution set. So we're going to have lots of possible answers. Basically, up to now, we've had one solution. We did some of this inverse solving already, all right? And I'm going to show once your frequency changes, that is, theta is no longer theta, but it's 2 theta, theta over 2, 5 theta. All right, we basically, there's a shortcut to basically regraphing the function, and it's adding plus 2 pi k to the solutions and integer values. We'll look at an example of that. So we're going to start with stuff that we've already done up to this point. So we've been solving some equations, right? It's what we did at the very beginning of chapter 6 with inverses. So I have this equation, and notice they have a range, all right? And almost all of them say the exact same range. Sometimes this range is adjusted, but it's almost always 0 to 2 pi. Because that is one entire period of sine, cosine, secant, and cosecant. And for tangent, that would be 2 full periods, right? And cotangent. All right, so 2 sine theta plus root 3 equals 0. So we solve this just like you solve any equation. Minus root 3, minus root 3. And there was one of these even on the quiz, almost just like this. Divide by 2, divide by 2. Sine of theta equals negative root 3 over 2. Now, here's going to be the slight difference. Since we're doing this for the range of 0 to 2 pi, I don't take the inverse because the inverse actually restricts the domain. That was one of the things we talked about initially. Instead, we're coming back around to thinking about the graph. And so we want to think about what's the graph of sine look like? Which one is sine? Remember? Sine is the most beautiful one. That's why we're starting with this. Sine is one entire period, so is cosine and all the rest of them. But it looks like a complete graph. Cosine starts peak to peak and just doesn't look as pretty. So I'm just going to put a couple of our base numbers on here. And now, okay, I want to, and then basically this is now I use kind of a combination of the unit circle and remembering what the graph is. So negative root 3 over 2, I don't need to know what that number is, but I know it's a negative, which means it's down here. All right. Since I know that the bottom is -1 and the top is 1, negative root 3 over 2 is somewhere in between those, which means how many times is it hitting my sine graph between 0 and 2 pi? Do we know? It's going to hit it once about there and once about there. That is the concept. All right. This number, this graph is not drawn to scale. Okay. But this number, negative, I forget what this number is, like 0.7. All right. This hits it twice. And that's what we're going to be looking for. The entire solution set. So now we kind of go back to the unit circle, all right? And basically you can look on your unit circle and find it. Where are all the places that sine equals negative root 3 over 2? All right. The easy way I always think about it is sine corresponds to positive root 3 over 2 at pi over 3. And I can think of the multiples of pi over 3. So the first one, pi over 3 corresponds to positive root 3 over 2. What's the next pi over 3 multiple?
2 pi over 3.
2 pi over 3. That corresponds to this one. What's the next pi over 3?
4 pi over 3.
Okay, 4 pi over 3, but it would be 3 pi over 3, which is pi. So I don't need that one. You're correct. The next one, oh my gosh, is 4 pi over 3. And then what's the next one? 5 pi over 3. And those are the two solutions. Right there is 4 pi over 3. Right there is 5 pi over 3. And then 6 pi over 3 is 2 pi. And so basically, you can do that every time, or you can just look on your unit circle and look for the y value corresponding to negative root 3 over 2. I don't care which way you do it. All right? I wanted to show everyone this so you get familiar with the graph because, again, I only have two numbers memorized. Pi over 3, pi over 6, 1/2 root 3 over 2. And then I can just find the multiples. All right, so you can do it that way fast, but you have your unit circle, which you can look at and correspond to. This then results, theta equals the solution set. We write that with the bracket parentheses, 4 pi over 3, comma, 5 pi over 3. Closed solution set. Those are the solutions that satisfy this equation on a range, right? And that's the big thing here. If this said, find these values from negative infinity to positive infinity, then it would be an infinite size solution set. If it was 0 to 4 pi, I would have two more solutions at whatever those multiples. 6, I don't know, what do we have, like 11 and 13, something like that, right? Or 9 and 11, something like that. Okay, let's look at another one. All right, solve the equation. Sine of 2 theta equals 1/2. Okay, so already now I'm adjusting. All right, so remember our graphing. When we had this value, all right, next to x or theta, what did this mess with on our graph? What did this number and what did we call this? Do we remember?
Amplitude.
Nope, amplitude's out here.
Doesn't that affect the period?
That affects the period. That was our omega or W, all right? That messes with the period. So instead of being our standard, this actually goes more times or less times, and I'd have to actually divide it out to see which one it is. Let's see, 2 pi over 2, so period becomes pi. So actually, now our graph is tighter in this period of 2 pi. So this, you can do this two ways. One, you can graph it, and we're trying to find exact answers, and then you can see how many times it hits, or this is the 2 pi k method that I was just talking about. So how we do this, let's start with our value, sine theta equals 1/2. So always get it down to solved. Okay, good, we're solved. All right, and then you think, okay, for the standard sine graph, up here at positive 1/2, how many solutions are we going to have? Two, once again, and it's usually 2. All right. The only cases where you have one solution is if you're at 1 or -1. Otherwise, if it's positive, there's 2 solutions there. If it's a negative, there's 2 solutions there. I mean, that's the concept of a periodic graph. Okay, so that becomes 2 theta, okay, instead of theta. All right, and the first one and 1/2 corresponds to what angle? For sine? Again, standard sine graph. Pi over 6. Right? So that one is pi over 6. What's the second one? What's the next like multiple of pi over 6?
5 pi over 6?
It's 5 pi over 6. Notice that because 2 pi over 6 is actually pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over. Oh, so the next actual appropriate multiple of pi over 6 is 5 pi over 6. So if this was just sine of theta equals 1/2, those are our solutions and we're done. But because our amplitude is shifted, I just said, because our omega is shifted, this is where we add the 2 pi k. What this helps us do, all right, is this helps us basically look at the period without fixing the period of the graph. And we saw, right, in order to adjust the period, we have to find 5 points, 5 basic points. Then you would have to find the adjustments of pi over 6 and 5 pi over 6 within those adjustments. So this is the faster way. Now I basically have 2 equations to solve. Now, good news, the solving of these is pretty easy as well. Divide everything by 2. Theta equals pi over 12 plus pi k. Similarly, theta equals 5 pi over 12 plus pi k. And in this case, I'm dividing by omega equals 2. Then all you have to do is pick constants for k, right? And not just any constants, we literally pick integers. And you start with the easiest one, k equals 0. And plug that in. So that means theta equals pi over 12 plus pi times 0, which becomes, oh yes, and then this whole thing becomes pi over 12. Same thing, 5 pi over 12 plus pi times 0, which becomes
Pi over.
oh, so the 0 one is the best one. So it gives me 2 solutions, pi over 12 and 5 pi over 12. Then I pick k equals 1. Okay, so now we have to do a little bit of calculation. So that becomes pi over 12 plus pi, which becomes 13 pi over 12s. And the other one is 5 pi over 12 plus pi, which is 17 pi over 12s. Now I'm out of space here. But that's fine. We can do it right here. And basically we keep going for as long as we want. So let's do k equals 2. Theta equals pi over 12 plus pi times 2, which is 2 pi, which becomes, what are we at? 25 twelfths pi. Now, at this stage already, I know this one is not a solution. And this is all because of my initial range that was given. It says find solutions between 0 and 2 pi. I know that 25 pi over 12s, right, 20 is greater than 2 pi because this number is larger than 2. And so basically you can always check that in your calculator, right? 17 twelfths is 1.6-ish, right? That guy is 1.1, right? That guy is half. That one is 1/10-ish, all right? So, all right, you basically pick numbers, and you can pick negative k's as well, but I know that as soon as I pick a negative k, I'm below 0. So all of this is about picking the range, which means my solution set is pi over 12, 5 pi over 12, 13 pi over 12, 17 pi over 12. And that's how that 2 pi k helps us, because you can do this graphically, right? But you have to find all those numbers, right? And that's the problem. It takes 5 numbers to set up the base 5 points of a sine cosine graph, right? Let alone trying to find the in between angles that usually we had skipped, right? This is the much faster way, but there are 2 methods. I don't even bother showing the other method because it takes forever. Okay. And so we've spent a lot of time, right, doing those identities and stuff. This, all right, is the last section of this chapter, and a lot of people actually start to appreciate, they like this because we're back to solving problems, right? We got into math because you like to solve problems, and those identities, I don't know what it is. People just say they're not fulfilled, even though I think there's so much cool stuff in there, all right? But most people even do better on this piece of this chapter. Now, notice the first half of this chapter, we saw there's still plenty of identities to solve, all right? All right, or to establish, all right, to basically prove this side equals this side. But this is back to actually solving problems. And here's the other thing. Don't forget that I can put, all right, so back to this one. Put this in your calculator, all right? Or sorry, put this one. Here's y1. y1 equals sine 2x. y2 equals half. And you can graph them and then find the intersection between 0 and 2 pi. Now, what's your calculator going to give you? Decimals. But you can verify those decimals with the proper solutions, right? Divide pi by 12, and that decimal will match the intersection of those 2 numbers. And that's absolutely, if you can find a way to fastly do that, that's fine too, all right? But it's a way to at least verify your solution. Establishing identities, you have the answer, you start with the answer, you end with the answer, okay? It's the in-between that everyone hates filling in. But this is back to solving, right? So, right, people feel that's a more tangible result, even though in mathematically, be aware it's not. It's the same, okay? But, all right, for those of you who are just here for, I was like, other reasons that you don't love math. Oh, whoops, I lost mine. 4 secant theta plus, okay. Okay. All right, so same as always, when we go to solve the problem, isolate what we're really, our trigonometric function now. And then just like with our graphing, do we ever graph the secant function? No. What do we graph to help us graph the secant function? Cosine. So same thing, reciprocal identity. And then flip it. And I actually have something that I can actually solve here. This also reinforces all that graphing we did, all right? But basically, from here on out, we're only graphing base functions. And the base functions that we are going to graph, sine, cosine, and tangent. All right, and a lot of times even tangent, you come back to sine and cosine. So basically, you should get really good at graphing the base function of sine and cosine. All right, so -1/2, that's down here. How many times does it hit the graph? 2. About right there, about right there. Just because of. For what angle does cosine equal 1/2, +1/2? What is it? pi/3. Okay, so +1/2, so the first pi/3 is right here. So which pi/3 falls between pi/2 and pi?
4 pi/3.
Almost, that one's right here. 4 pi/3 is greater than pi, right? So what's the other one? 2 pi/3. And, all right, is theta adjusted? Right? Is there an omega with theta? No, which actually means the base graph is our solution, so I don't need to do the 2 pi k part. And so those are the best ones. So my solution set, theta equals 2 pi/3, 4 pi/3. If theta is not being multiplied or divided or like actually added, doesn't matter, like, because that'll easy adjustment. All right, then basically all you have to do, all right, is graph the base function. All right. And already, so you can tell which ones have more work from the beginning, right? Is this one gonna have more work? Yes, because I mean, we actually don't worry about it being a half angle. You're absolutely correct. This is a half angle, but theta is adjusted. The fact we recognize that adjustment is excellent. But the fact that theta is adjusted, I have to mess with the 2 pi k's. All right. And I mean, I can look at all of them, right? Like, oh, I want to solve that one. I want to solve that one. I do not want to solve that one, right? Because this just becomes more work. So you can identify that from the beginning. All right. And the good news is, at least we already did some of this. -√3/2, this is literally what we did above. We already identified those angles. This one is 4 pi/3. This one is 5 pi/3. So we take our multiple solutions, and that's the important part. The other big issue I see is people leave off the second one. They just find one solution, all right? That's why I always want to draw the graph the first time to make sure it hits twice, all right? So when I do this adjustment, I need to make sure I have both of those angles. Okay, So then we get to solve this and we multiply everything by 2. So theta equals 8 pi over 3 plus 4 pi k. Pi over 3 plus 4 pi k. So already this looks kind of weird, right? Because I'm adding 4 pi to my solutions. In fact, 8 pi over 3, that's already outside of 0 to 2 pi. Which is why this one, notice the solution set it gave us, all right? It was not 0 to 2 pi, so make sure you're paying attention to that. This solution set is from all solutions between 2 pi and 8 pi, included both ends. So a lot of times be aware that it actually says, oh, that one says included. Oftentimes, it actually says less than, right? So it's because it might be a double solution, right? Because we know things like sine and cosine, their start and their end is 0 and 2 pi is the same number. So always pay attention, see if that part matters. Okay, so now we test some k values and I always start with k equals 0. That gives me 8 pi over 3 for the first one, 10 pi over 3 for the second one. All right, so 8 pi over 3, which is above 2 pi, and that is in our range. So basically, we need to test until we get to a number that is 8. All right, so plus 4 pi, which is 8 pi over 3 plus 12 pi over 3, 20 pi over 3. And then the other one, 10 pi over 3 plus 4 pi. Is 10 pi. All right, so basically already at k equals 1, 22 thirds, because I know 24 thirds, that's 8 pi, right? 24 thirds, so I already know that if I try another one, I'm outside my range. So you could always test the other one and then just, double check the fraction. I mean, it's easy to do in your calculator, but I already know I'm almost at 8, which means that the next solution, k equals 2, I know that won't work. And so hence, theta equals 8 pi over 3, 10 pi over 3, 20 pi over 3, and 22 pi over 3. Do we like this a little bit better, Macy? You
So much
like
better.
solving better? Okay. I was thinking of you when I thought of.
I love graphing, the rest of it's not
All right. Okay. But here's the other thing. The techniques we learned from establishing identities still apply here. When I go to solve this, all right, I need to solve this. How should I solve this? We're now solving equations. I want this to say sine theta equals something. This is factoring all the way, okay? And that's good because we want to start recognizing that. So just like we did before, let x equal sine theta. So I have 2x squared minus 3x plus 1 equals 0. And then what approach do we take that we love? How do I factor this? Charlene?
good. Diamond?
Diamond. All right, something I saw that I think you tried. You like to go straight to the parentheses, huh?
Yeah,
I do this sometimes.
You do that. Okay, I do that on the easy ones. This is not any okay, this is easy-ish, but I was like, I'm all about the diamond because it just takes the guesswork out of it. So what multiplies to 2 and sums to -3? What two values?
-2 and -1.
-2, -1. So this becomes 2x squared minus 2x minus 1x plus 1 equals 0. And then, what do? So the diamond makes it worse temporarily.
You factor by grouping.
Factor by grouping. Group two terms, group two terms. What do we pull out of the first two terms? What's that leave?
X -1.
What do I pull out of the second two terms?
-1.
Oh, very good. -1. You gotta get those signs to match. So I'm gonna pull a -1 because that becomes then x minus 1. And then 2x minus 1 times x minus 1 equals 0. And then we can do one more step of solving before we plug it back in. So x equals 1/2 and 1. Right? And that's algebra all the way. All right? No trig there whatsoever. I was like, that is algebra solving like 101. All right? And that is still something we're going to use all the time. All right? Okay, so now the trig part. So that means sine theta equals 1/2, right? And sine theta equals 1. All right, so our standard sine graph. So this is actually awesome news. All right, we haven't had this yet. Sine theta equals 1. What angle is that?
90.
That's right here at pi/2. And this is also the situation. How many times does the graph hit 1 between 0 and 2 pi? Once. That's the exception case. All right, almost everywhere else, right? It is twice. It hits 0 twice between 0 and pi/2, excluding 2 pi. All right. Oh, sorry, 0 to 2 pi. All right. If we were including 2 pi, it would hit 3 times. That would be the only other exception. All right. Okay, and then 1/2. How many times does it hit the graph? Twice, right? So we're back to twice. And actually, we did sine of 1/2 already. What are the angles there? All right, what does our unit circle give here?
pi/6 and 5 pi/6.
Pi/6 and 5 pi/6. Is theta adjusted here? Is theta anything besides 1? No. Which means those are the solutions, and hence that is our solution set. And then be aware that it's not massively important, but typically when we write numbers, we write them low to high, right? So pi/6, then comes pi/2, then comes 5 pi/6. I was like, technically, if they're all in there, it's still correct, but we want to be pretty in math. Okay. 3 cosine theta plus 3. All right. The other kind of trick we need to do is when we're solving equations, I don't want 2 graphs. if I can avoid that. So whenever possible, try and get your trigonometric functions, right, to the same angle and ideally the same trigonometric function. Does anyone see anything that I can mess with to get to one trigonometric function or another? So ideally, I want this in all sines or all cosines.
We changed the sine squared data into cosine, the fundamental identity.
Yes, all right, using the fundamental identity. And this one actually only can go to cosine. I can't convert this to all sines because there is no direct function for cosine going to sine. But there is one for sine squareds going to cosine squareds. So yes, using the fundamental identity. And specifically, sine squared theta equals 1 minus cosine squared theta. All right, so the adjustment of the fundamental identity. Now this becomes 3 cosine theta plus 3 equals 2 times 1 minus cosine squared theta. And this is when we're solving, right? So this is a different thing than when we're establishing identities and we wanted sines and cosines, doesn't really matter. When you're solving, you want to get it down to one trigonometric function because I don't want to make multiple graphs. And a lot of times the zero product property doesn't work if you have two graphs. Sometimes it does, but it has to be like perfectly. Okay, and then this is a matter of, once again, once I have everything in the same one, I can already see this is quadratic and probably something factorable. So let x equal cosine theta. And then I have a quadratic to solve. And with all quadratics, we get them equal to 0. And that's almost the same diamond we just had. Is that exactly the same? Oh, no, off by a sign. So it'll be pretty close to what we had. So yeah, almost the same numbers. X equals -1 now and -1/2. So cosine theta equals -1 and cosine theta equals -1/2. Okay, so -1. Again, here's the exception that hits the graph once. At what angle? Pi. It's literally one of the two numbers that I ever put on the graph. Right? Because I try and just put the middle point and the end point, because that's all that. When you're just drawing a base function, I have 0 and then 2 more points because I don't care about the rest. Unless I need them to help me identify. Okay, then the other one, cosine theta equals -1/2. And I think we did this one actually too, right? So you see they keep coming back around. Right? -1/2 hits twice. Yeah, actually, I know we did. Because it's pi/3 would be the +1/2 version, and then 2 pi/3 and 4 pi/3. Theta, again, is not adjusted in either of these cases. These are the best ones, all right? No 2 pi k's to worry about. So, hence my solution set, theta equals 2 pi/3, pi, 4 pi/3. And so we have, again, it is nice to get to problems that, oh, theta equals a number, right? I was like, we're actually back to finding angles. All right. We got time for one more. We'll finish these other ones later. Actually, I was like, now that I look at this closer, this actually doesn't look nearly as bad. Because cosine 2 theta, that is a double angle. And if I could ever put this into something that I can solve back to my original angle, because I have a theta and a 2 theta, which means I need to get these to the same angle. Either A, convert that to a double angle, right? Convert cosine 2 theta to 2 theta somehow, or convert cosine 2 theta to thetas. And we do have the double angle formulas. Cosine 2 theta, all right, now remember there are 3 versions of this formula. The one I use all the time is cosine squared theta minus sine squared theta, but I don't want to add in that. So is there another option to get into only cosines?
2 cosine squared theta minus 1.
Ah, so actually I can convert, all right, that double angle cosine 2 theta to purely cosines in order to be able to solve this. So that now becomes 2 cosine squared theta minus 1 plus 3 equals 5 cosine theta. And now once again, what am I looking at in a more complicated version? What is this whole equation? It's a quadratic, right? Once again, this is just a fancy looking quadratic. So let x equal cosine of theta. And then I can actually start simplifying. Let's see, 2x squared, bring that over, minus 5x plus 2 equals 0. Okay, and now we have a diamond that is different. It's 4 and -5. And notice, none of these diamonds are super complicated, right? So what multiplies to 4 and sums to -5?
-1 and -4.
-1, -4. I was like, right? No, this isn't hard algebra, but it's all the pieces together, right? All that math knowledge you get to use, all right, is what makes these feel overwhelming. But one piece at a time, one step at a time, one breath at a time, right? Don't panic. Okay, so this becomes 2x squared minus 4x minus 1x plus 2 equals 0. Group, group. 2x pulls out of there. -1 pulls out of the second one. So we've got to flip our signs. And then once I have it solved algebraically, I can come back. Cosine theta equals 1/2 and cosine theta equals 2. And let's start with the 1/2. So finally, a slightly different, not -1/2. All right, once again, it hits twice there and oh, way over here. Okay, so for what angles is cosine theta 1/2 between 0 and 2 pi?
Over 6.
It's not pi over 6.
Oh, sorry. I have 3.
Pi over 3? And what's the other one? 5 pi over 3. It's way over here. All right. And cosine is kind of annoying like that, which is why I like sine better. So pi over 3 and 5 pi over 3. Okay. So that one, piece of cake. All right. Where is cosine theta equal to 2? Oh, never. Oh, see, that's kind of tricky. All right. And that's why I was like, this one, a lot of times I don't put the -1 to 1, but I put it on here just to further emphasize that. The maximum of, right, a unadjusted cosine graph is 1. All right. Which means, all right, and that happens, there's no solution to this one. All right. And that happens all the time. Do we still have a solution overall? Yeah, because we have cosine theta equal to 1/2. All right. But this type of thing, it's often that the other one will just be extraneous. All right. And make sure, all right, don't get stuck on that forever. Ideally, notice that. All right. And so, hence, theta equals pi over 3 and 5 pi over 3. All right. We will pick it up right there. We will start at example 8 next class. All right. So next Tuesday, we will basically finish the next bunch. What do we got? Up to 12. All right. So examples 8 to 12. All right. We will finish next class. And the big thing is that they actually, right, going to start getting more interesting, a little bit longer. But